All right, so I'm ready to do some more examples. In this case, what I'm going to do is I'm going to have a region bounded by y equals x squared and y equals x cubed. Still in the first quadrant. This time we're going to revolve it around the y-axis. Now that's the big hint here, is again, I'm trying to get across to you that if it's doing the x-axis, write it in terms of x. In this case, it says y-axis, so I'm going to have to do this in terms of y. And that's just the big hint to you. So, but again, first things first, draw the graph and see what happens. So, I'm going to go ahead and start drawing the graph. Now, in this case, y equals x squared shouldn't be that hard to graph. What I'm going to go ahead and do, think about it. If I do 0 squared, I get 0. Let me go ahead and do 1 squared is 1. So that should be right about here. But if I square 0.5, it's going to give me 0.25, okay? Let me go ahead and just go ahead. I'll try to type in some others. So if I do 0.25 squared, that gives me 1 over 16, which is 0.0625, so it's really, really low. And if I do 0.75 squared, it's giving me 9 over 16, which is 0.5625, which is just barely above the halfway mark. So my parabola looks like that, okay? Now, again, that is y equals x squared. And I can keep it going if I wanted to, but I really don't need any extra at this exact moment. But what I am going to go ahead and do is try to think about y equals x cubed, okay? So if I do x cubed, again, 0 is going to be 0, 1 is going to be 1. So I know where those intersections were going to be right off the bat. What I'm worried about here is what's happening in between 0 and 1. So that's what I'm going to go ahead and double check, is what happens if I do 0.5 to the third power. I get 1 over 8, which is 0.125, which is right here. It's halfway between 0 and a quarter. If I do 0.25 cubed, I get something even smaller, which is 0.0156. So it's really, really low down here. It's almost 0. Even if I do 0.75 cubed, I'm still not getting a very big number. It's still below half here. And so I've got this, I'm going to call it a sliver. It's very, very small region. It's almost non-existent because they're so close together. But there is still a region here nonetheless, okay? So again, that blue one is y equals x squared, and the red one below it is y equals x cubed, okay? So now that I've got those graphed, I know which one's on top. The blue one's on top, the red one's on the bottom. But like I said before, I'm not doing this in terms of x's. I need to do this in terms of y because it says the y-axis. And so I'm not actually going to look at what's on top versus on bottom. I'm going to look at right versus left. And if I look at the one on the right, it's the red one. So when I switch y equals x cubed, I'm going to turn it into x equals the cube root of y, which is y to the 1/3. That's going to be the one that goes first. Whereas y equals x squared, which is going to become, oh, excuse me, I should write an x first, the square root of y, which is y to the 1/2. That's going to go second because that's the one on the left. Right first, left second. So here's what I'm going to do. I'm going to go ahead and start working on the area part. The area part is going to go from 0 to 1, where they intersect. 0 and 1 are my y values because I'm using y. And again, y to the 1/3 first minus y to the 1/2 second. Again, the one on the right goes first, the one on the left goes second. Now, if you wanted to do this in terms of x's, that's fine for the area, but when I go to find the volume, it's not going to work. It's not going to give you the right answer, okay? So make sure you're careful here. All right, again, this problem could, like the area could be done x's or y's. I'm doing y's because I'm using y-axis later. All right, so I'm going to go ahead and start working on this. So when I integrate, this is going to become y to the 4/3. So I'm going to actually divide by 4 and multiply by 3. Then I'm going to do, that's going to become y to the 3/2. So I'm going to divide by 3 and multiply by 2. And I'm integrating from 0 to 1. Again, if I plug in the zeros, it's not going to matter. I'm just going to plug in the 1. So 3/4 of y to the 4/3 minus 2/3 times, whoop, I should plug in a 1. Silly Mr. Harold. 1 to the 3/2, okay? So that's just going to be 1. That's just going to be 1. So I'm going to end up with 3/4 minus 2/3. I'm going to rewrite those in twelfths. So I need to multiply that by 3. So it's going to be 9 over 12 minus, multiply that by 4, 8 over 12, which is 1/12. So like we said, it's going to be a really small area, 1/12. 1 divided by 12, I know is going to be repeating this, but it's 0.083 repeating. Let me repeat that again. 0.08 with the 3 repeating. So it's a really small number, but we figure that it's a really small area. Now here's the thing. When I revolve it around the y-axis, okay, what's going to happen is I'm going to get something that looks almost exactly the same over here. It's still going to be another sliver, but here's the thing. Now it looks, and this looks almost exactly like a bowl would. You've got the outer edge of the bowl, you've got the inner edge of the bowl, and you know, you can put the soup in here. Mr. Harold likes ramen, just saying. But so here's the thing. So we actually do have a bowl here, but we notice that it's going to have a wider part here and a really, really thin part down here at the bottom and in the corners. Okay? So this is our bowl, and in this case, again, we do have an outer radius and an inner radius, because notice if I were to try to, you know, look at a slice of this, it's going to have a really big hole in the middle. We're going to have a circle all the way around, but then there's the hole where you would put the soup. Okay? So this is going to definitely be the washer method, and let me repeat again. I'm going to use the outer radius, which in this case is the red line, and I'm going to use the inner radius, which is the blue line. So again, you know, y to the 1/3 is going to go first, y to the 1/2 is going to go second. Hopefully you guys remember. I'm going to write down that formula again one more time just so I remember it. If I'm doing the washer method, we're going to do the integral over the bounds, again, 0 to 1. And what we're going to do is pi times the big radius squared minus the little radius squared. And in this case, again, big one is y to the 1/3, the little one is y to the 1/2. So I'm going to do 0 to 1 of pi times, let me write this very carefully, y to the 1/3 squared minus y to the 1/2 squared. Wait a second, hold on, pause, give me a second. Y to the 1/2 squared, doesn't that just make 1? So that's really just minus y. Y to the 1/3 squared, that makes y to the 2/3. So that actually makes my life pretty simple in this case. I don't have to worry about another fraction. All right? So before I get into the integration part, I just wanted to make sure I pointed that out. I simplified it ahead of time. So now I'm going to go ahead and again, I'm going to pull out the y, or the pi, excuse me, I said y instead of pi. I'm pulling out the pi, and then I'm going to go ahead and integrate. So y to the 2/3, that's going to become y to the 5/3, okay? So I'm going to divide by 5, multiply by 3. All right, that y is going to become y squared, so I'm going to divide by 2. All right, and again, we're going to integrate from 0 to 1. Again, when I plug in the 0, it's not going to really matter. It's not going to change anything, so all I have to worry about is plugging in the 1. So I've still got the pi on the outside. So 3/5 times 1 to the 5/3 minus 1/2 of 1 squared. Again, I don't need to worry about the 0 part because it's just going to make 0. All right, so pi, and that's going to be 1, which is 3/5. That's going to be 1 squared, which is 1, so minus 1/2. I'm going to go ahead and make that common denominator of 10, so I'm going to multiply that by 2. I'm going to have 6 over 10. Multiply that by 5, so 5 over 10. So we're going to have pi times 6/10 minus 5/10, which is 1/10, or pi over 10. 1/10 of pi or pi over 10. Either way you write it, that's my final answer. Now notice again, make sure you are very, very careful and don't try to change the pi to a decimal. Leave it as pi over 10. That is the final answer here. Hopefully that helps in understanding the difference between the disk method and the washer method. I've got some more examples coming right up.